Good morning, guys, and perhaps good afternoon and good evening. So welcome to the fifth talk hosted by the AI Talks. And today we are very happy to have our speaker, Chen Ting from Google Brain. And Chen Ting is currently a research scientist in Google Brain, and his research interests include self-supervised representation learning, generative modeling, and efficient architecture designs. And before joining Google, he received his PhD in computer science from UCLA. And in today's talk, Chen Ting will share his latest research about how to use continuous diffusion models to generate discrete data. So Chen Ting, you can start whenever you are ready.
Yeah, thanks, Kaya. Yes, my pleasure to present today of our recent work, Bit Diffusion, generating discrete data using diffusion models, particularly with analog bits and self-conditioning. So this is a joint work with Rui Xian, Zhang, Jeffrey Hinton from Google Research Brain Team. Okay, so why do you care about generating discrete data? Because this particular problem has a wide application. So for example, when you're modeling the text sequence or documents or generating them, they have a wide application. And modeling other kind of sequences such as DNA sequences, or other discrete data in recommendation system. Sometimes even images can also be modeled as discrete data if we apply some kind of condensation, and then many others. So if we have an approach that can model discrete data well, then we can definitely have a lot of useful application with it. Now this is a quick review on what the existing discrete generative models are out there today. So I put them into two categories, kind of with my subjective perception. So one category is the model that kind of work at the simple discrete data. Examples including variational autoencoder, basically autoencoder with a Gaussian prior, and then this flow-based model where you define a reversible transformation, so you can mapping the noise some prior distribution to the data, and GANs, which basically is a distribution matching mechanism with a discriminator. So with a bit more complicated data, they don't tend to work very well, at least at the current stage. So out on the market, the existing best model that you can use for generating discrete data is autoregressive model with transformers. I guess many of you already know, like GPT and other language models, they all based on this category, and they model discrete data very well. And in fact, can be applied to other discrete data that's non-language based, right? So the basic idea of this approach is that you're just looking at the previous token and predicting the next token one at a time. And typically you can use a transformer with attention masking to do this efficiently. But essentially you're predicting one token at a time with a cross entropy loss, right? Now this sounds great. GPT is very powerful. We know language model are useful, but they still have some issues with scaling. So let me show you like what the issues are. So one is the training computation and memory can be quite costly. So it is quadratic to the dimension of data. For example, like the sequence length, or if you use it to model the image as a long sequence of discrete pixels. So if you have a transformer, it's quite obviously that you typically will get quadratic complexity, and then the memory-wise is also quite expensive. Yeah, so and in terms of inference time, when you want to generate from such autoregressive model, you generate one token at a time. So the total number of sequential steps is often the same as the dimension of data. Now, if you have 1,000 tokens to generate, like usually in language model, you don't generate the whole book, right? So you can still do it. So in for some practical application, it's fine. But in other cases, if you have a high dimensional, if you want to generate tens of thousands or even more, millions of discrete tokens, let's say consider the DNA sequences, right? So how do we do that efficiently? So with autoregressive model, I think that would be quite tricky. So if we look at the other, recently emerging generative model for continuous data. So here we consider continuous data. You see this a quite different paradigm of generative model based on diffusion models. They're different from autoregressive model in two aspects, at a high level. So first, they can model much higher dimensional data without running into computation and memory issues, because they don't generate the one token at a time. That's not requiring, those attention masking to do the autoregressive, like teacher forcing training. So and during the generation, diffusion model iterative refine samples with a high degree of parallelism. So the total number of sequential sampling steps can be much less than the dimension of data. Like you're generating an image of 512 by 512 or 1K by 1K, it has like more than a million of pixels. You don't need to go over a million the image generation a million times, right? You just go over maybe 1,000 times, right? So this is a big win. But what is a diffusion model exactly? And can it be applied to discrete data? So the thing I'm describing here is mostly for continuous data, but can we apply it to discrete data? Before answering that question, let's look at what are the diffusion models, at least from some intermediate level of understanding. What are they? So diffusion model, in my opinion, basically it learns a series of state transitions to map noise from a non-distribution like Gaussian distribution, to samples from the data distribution. So for example, you can start with the noise and then gradually refine, and in the end you get a clean image back. So in order to learn this mapping from noise to data, right, it's quite counterintuitive. Like how do you learn the distribution, mapping from noise to data? But we can first define a mapping from data to noise. So this is given as below. So X0 is basically the data samples, and epsilon are samples from the prior distribution, such as Gaussian. So you do some kind of interpolation. So you do a so-called variant preserving interpolation between them. So if you go all the way to noise, right? If you have a 1 here and 0 here, you go all the way to data. And if you have 1 here and 0 here, then you go all the way to noise. So by manipulating the time t here, which we can consider it between 0 and 1, then gamma is a transformation of that. Again, the output of gamma is between 0 and 1. And then you can take a data point and gradually go to noise. Now, how do you go back? So you can go from data to noise with ease, with such a formulation. Now, going back, let's look at during the inference, how do you go back from noise? So during the inference, you don't have data, so you only have noise sample from some Gaussian distribution. Now, I think what initially diffusion model initially wants to do is that you make a bunch of transitions from xt to xt minus some small delta every time you take a small step, and then eventually when t equal to 0, so you go to the data samples. So the beauty on the recent progress has been that instead of directly model this process from xt plus some delta to xt, that you every time you estimate either the noise or the data itself. So the noise and the data are in here, right? So you at every state you make an estimation to the data or the noise, and then you use them together to jump a little bit closer to the data state. And then repeat this process, you are able to eventually mapping the data from mapping from the noise to the data. Now, how do we train such a function? Because the key thing here is, given a state, a noisy state, you should be able to predict the data on the noise. And then this is, if you are able to do that, then the jumping from, given these two, the jumping is quite straightforward to XT. But in order to do that, you have to learn such a mapping from the noisy state to estimate of the data on the noise. So here I use data as for simplicity. So basically, the loss would be, you take a data point and then you sample a time, and then you make a noisy data, and then you learn the denoising network to estimate, the input clean data. So that's essentially the loss function is. And once this is learned, then you can use the denoising function to make estimate and make the jump from noise to data. Okay, so maybe it's a little bit too abstract. Let's maybe look at the exact training loss and the inference procedure or sampling procedure. So this is actually quite simple. So you take an image or some data point, right, X, and sample a time t between 0 and 1. And then you also sample the noise, from a standard Gaussian distribution. And then, you do this forward corrupting of the data, as we mentioned before. So you have a noisy state, right? Now you take this noisy state as input along with the time step t to the network, denoising network, which estimate the original data, clean data. Now, because it's an estimation, so you want it to be as close to the original data as possible. So this X should be X original data. Now this loss would be the L2 regression loss. So that's all it is with diffusion model for the training, which should hopefully be very simple. And then in the inference is actually also very simple if you ignore some chunk of the code. So what exactly you do is, at the sampling time, you have to specify how many reversing steps you want it to take. But you start with the noise, from the standard normal distribution. And then you go backwards, you determine the current time step and the next time step, which is smaller than the current time step to jump to, right? Now so because initially you start with XT, now, you assume ST is in this T now step time, and then you make a prediction of X0. So what would be the estimate of the data at this point? Now with the current state and then the current estimation of the data with the time steps, right? You can make a jump to XT that's closer to 0. So you make it closer to the data. So you gradually, over different steps, you gradually jump closer to the data. So you notice here, you have this jumping. Basically, what happens is that you take the current step, let's say ST minus plus delta, and then estimate X0 naught, which basically is this X predict. And then, you jump to the next state. And how you make the jump is described by this, you're using the DDIM rule or DDPM rule. But once you have these things estimated, this is just some deterministic. So, I mean, this is just some program without any parameters to make a jump. And one thing to notice here is we use the formulation I use here is, it is this use a continuous time formulation, which is more flexible. So the time is between 0 and 1 continuously, instead of the original discrete time formulation. This is a bit more flexible, but in essence, they're quite similar. Okay, so that's basically the diffusion models for continuous data. Now the question comes, can we model discrete data with diffusion models? So if we directly use above algorithms, the answer is no. So it doesn't work on discrete data. Now people, smart people have proposed a few extensions of above algorithm. So you can actually model discrete data, but that's a different type of diffusion model. The key difference is that they have to change the continuous state space model to a discrete state space model. What I mean by continuous state space is like, the XT basically image of different stage at different time step. They are all continuous because they are kind of, you can see here the interpolation is between the data and the Gaussian noise. So Gaussian noise is continuous, and then this interpolation is continuation. So they are continuous, continuous state space, and they have to change that to discrete state space to work. But although they can do that, but I think somehow the results are still not as satisfactory compared to, let's say, an autoregressive model, which we will see later on. So in this work, what we do is we also give a yes answer, but we do not need to change the a continuous state space to discrete state space, right? So that's kind of the key difference with existing algorithms. Now, the question is, how do we do it? So the first technique we propose is the analog, so-called analog bits. So it might sound a little bit confusing because bits are typically, logical bits, or digital bits. But why is it analog? So let me explain. So most of, all the discrete data, they can be represented as binary bits. Because if you look at language modeling, every token has ID, and the ID is an integer, non-negative integer, which you can turn into binaries, right? And then if you model binaries as digital bits, it means you can only take 2 values for every bit. But what we propose here, very simple, is to cast binary bits into real numbers. What that means is that then you directly model them as continuous numbers that happen to be 0 and 1, right? So let me give this example. So in the training, again, I'm using diffusion models, but in principle, this could be other continuous generative models. So you take a token ID equal to 5, then you turn it into bit, which is, a function, but it's very easy to understand that this mapping is like net. And then, you cast this as real numbers. Of course, we can do some scaling and shifting. So let's say we map it into -1 and 1. So now you notice there is 1.0 and a -1.0, because these are real numbers that happen to be these 2 values, okay? Now you take that as input to diffusion model, which model these continuous numbers. And now during the inference time, what you're going to do is you sample as if you have continuous numbers. Now you hopefully the model will generate something like that, -1.05 or 1.01, because they are quite close to the 2 binary numbers. Hopefully that's what happened, but we will see if that's something that indeed happened when we apply when we train this model. But if you have something like that, then you can simply do a thresholding, right? So it's quite obvious this should go to 0 and this should go to 1, okay? And then you do a reverse, a transformation from bit to integer, and here you go, you get the token, discrete token back, right? So that's basically an idea of analog bits. Now you might think this is a bit, interesting, but why would it work? Because underlying the data is discrete. You try to model, but now you have a continuous distribution. So let me give you an example that to maybe facilitate some kind of intuition in the space. Like, you have a continuous distribution, 1D distribution, like a Gaussian here. Now, let's say if you want to just generate a Bernoulli distribution, like generate some 1D binary data. Now, if you split, so of course, this is a deterministic model. Now I'm illustrating here, but even stochastic, it will be similar. So you split this Gaussian into 2 parts. right? So anything, when you sample Gaussian from this part, you're going to map into -1. Otherwise, you map it to 1. So you have a, mapping from noise, which is the Gaussian, to the data. You can do 0.5 probability of Bernoulli sampling of 1, right? So if you want to do other things like 0.7, you just cut this Gaussian in different locations, so then the mapping will be the mapping on the sampling procedure will reflect, the desired underlying, Bernoulli distribution. Now, if you have like many dimensions, generally high dimensional discrete data, they'll be quite different like that. But I think underlying the intuition is similar, where you can map the continuous distribution to, discrete distribution with a continuous generating model. Okay. Now, how does it work in practice? Like, if you have a diffusion model for continuous data, now you suddenly wanted to do a discrete data modeling with it. So these are 2 lines of code that you add to original, diffusion model. Whereas at the beginning, when you have the data that's discrete, you just turn it into bits, and then you cast it as floating point bytes. You do some shifting and scaling optionally, and then all the rest are just standard diffusion models. And now during the sampling, you just need 1 line of code change, which is that you still start with the continuous normal distribution, you generate all the samples, and then you take the generated samples and then threshold it to get a binary bits, and then you turn it into integer, which is the token ID that originally presented for representing the discrete data, right? So, okay, so that's all for the analog bits algorithm, at least the basic version. So how do we know it is good? So we have to evaluate it on some task. And one task that we found particularly useful is the discrete image generation. So typically, image generation is you just model it as continuous pixels because the intensity of pixel reflecting some meaning, right? Like, 0.1 is closer to 0.2 compared to like 0.6. So, but you can also consider them as discrete tokens. So every pixel will be represented as 3 numbers. So with 64 by 64 images, you have 12K discrete tokens, so which is quite high dimensional already. If you consider in the as a language modeling context, so you have a sequence which is 12K length. And then this is easier to evaluate because there is a FID metric which people typically use to evaluate and generate image quality. Now we consider 3 discrete encoding for pixels. So the first one is, because every subpixel intensity is between 0 and 255 or 256, and then you can basically represent it with 8-bit, right, quite easily by just mapping the integer uint8 number into bits. Or you can do a gray code encoding, which means 2 number like 5 and 6, they only differ by 1 bit. Any 2 adjacent integer only differ by 1 bit in the representation. And then the other final one is that you take the uint8 representation and then shuffle it. So originally, 1 might map to 0001, but now you map 1 to any random bit. That's but the mapping is unique for each of the integers, but they are random. So one way to look at this different encoding is that look at the Hamming distance between the discrete bits, binary bits, and the absolute difference in the pixel intensity. So you can see with uint8 representation and the gray code representation, you have this correlation where if Hamming distance is small, is large, then the intensity difference is large. So roughly you have a correlation, but still remember the variance is quite large. So you typically have something that only differ by 1 Hamming distance, but the intensity could be quite large actually. But if you go with Ewing-8 with random shuffling, now you eliminate those correlations. So basically, this is a categorical setup where two binary bits, two set of binary bits, they have no correlation in terms of their pixel intensity. So this is as if every subpixel 0 to 256 can be considered as a discrete token in language where you cannot measure their distance. Okay, so now let's compare to state of art, including autoregressive models and existing diffusion models. So we can see, so one thing I will pay most attention to is the categorical pixels, where every pixel has no correlation with the other pixel in terms of their binary representation. So the state of art is 12 in terms of FID, and smaller is better. This is held by autoregressive transformer trained by OpenAI. And what we did here is this one, Bit Diffusion, and we basically almost half their FID numbers. So I would say this is an improvement by large margin. And then what's worth to emphasize is on ImageNet 64 by 64, we are also doing well, as shown before below here. Like if you model image as continuous pixels, which is the most efficient way, because pixels has some intensity correlation. But if you model it as categories, you still get a decent FID. We don't have any baseline to compare here because we don't know people have reported the FID. I think previously the model on discrete ImageNet 64 by 64 do not yield very strong samples as far as we know. And then another thing to emphasize here is for categorical pixels. So we use 100 sampling steps that generating 64 by 64 image, which contains roughly 12K tokens. But you sample it only on 100 steps, not 12K step. If you were to do it with an autoregressive model, you have to generate 1 token at a time. So that's an improvement. So just to convince you, the samples are actually pretty good when you model image as discrete categorical pixels. Here on the left is continuous modeling, DDPM, which gets a very good FID. And then this is the modeling as a categorical. The FID is larger, which is worse, but you can see in the image quality is actually also very good from eyeballing things. So each row here, I should mention, each row here is a class. Okay, so another thing, like you can take these generated analog bits and asking, are they in the middle? Because we have analog, the data is, you can make it -1 and 1. Now for the generated data, is it going to be very close to -1 and 1, or there are something in between? So as you can see here, for 3 different discrete encoding for the pixels, they all generate data analog bits before thresholding. So after thresholding is either 0 or 1, right? So before thresholding, they could be anything because it's continuous modeling. They could be anything, but they choose to be quite committed to either -1 or 1. I mean, either in this case, there's a little bit of bump here, but it's still far away from the center. So this suggests the model learns to commit to either mode quite well, and also suggests that quantization error, like you take this distribution and then you threshold it, you almost see no loss, right? So the quantization error might be quite minimal or near none. Okay, so that's image generation, which is a good benchmark, but people could still measure, generate image in continuous space, right? There's no, there's little real reason to generate images in discrete, as discrete data. But here, if we want to generate a test like image captioning task, so we will have a little bit more realistic task. So we compare this with autoregressive transformer for image captioning on MS-COCO dataset, which, as to mention, is not a very big dataset. In nowadays standard, it's actually a quite small dataset, but just for the proof of concept, we are able to achieve similar performance to autoregressive transformer on this dataset with relatively few inference steps. So it's also worth to mention that we are actually modeling, although the sequence here you can see is not very long, but we're actually modeling 960 bits because there are a lot of paddings as well, and the sequence are different lengths, But even with so many bits we are modeling, we only need a few inference steps. It can produce quite reasonable samples. Like, here, when you have 1 steps, you can definitely see the artifacts that it does not generating the words well. And then you increase it to 5 and 10, it kind of already generating sentences that's meaningful to the describing the pictures. Okay, so other forms of analog bits can be utilized as well. Like instead of using binary bits, we could use one-hot representation for the analog bits. And also, as alternative to L2 regression loss, we can also use sigmoid and softmax loss. I will not go into details here because preliminary results have not shown such much gains over standard analog bits. But in the future, this is definitely worth exploring. Okay, so that's the first proposed technique based on analog bits. And then the second one we propose is self-conditioning. So conditioning is a useful technique for improved diffusion models. So typically a conditioning variable is some external sources such as class labels or some no resolution images from another network, as you can see in these cascade generative diffusion models. But here, the question we ask is, since the inference procedure is iterative, right? You generate one step and another step until you get to the clean image. So can we use previous generated samples as the conditioning signal, which, because it's using previous generated samples, so we call it self-conditioning. More specifically, so instead of throwing away, so remember every time at a state, you're going to predict, the x0 or noise, which can be transformed to get x0. Every time you predict it, and then you throw it away because you make a transition in the standard case to another noisy state, and then you make another estimate. Now the change here is pretty minimal, which is that instead of throwing away previously generated samples, or previous estimate of the data sample, you're going to condition on it. And then the conditioning can be done by simply concatenating, the predicted x0 not with, xt here to make the prediction of the next sample. So this is a big abstract maybe, but let me show the algorithm behind it. So basically during the training, what you need to add as addition to analog bits transformation is this part. So now instead of so here we first go in the one forward pass with x predict equal to 0, and then we concatenate it with the corrupted noisy state, and then to make a one prediction x predict. Now we use net1 as the conditional signal during the training. So we concatenate this noisy state and the one-step prediction of the data together as the input to train this denoising network to take advantage of this additional conditioning factor. And this in the training only increase the compute by less than 25%, usually less than 10%. And then in the inference, this is basically coming for free. So every time you make a prediction, so an initial, you don't have any estimate of x0, so you use a 0 as an estimate. And then if you make an estimate of the x predict, you're going to use that for the next iteration or next step by concatenating the current state and the previous estimation. And that's it. That's you basically do a concatenation. So you count, this basically count with no cost during the inference time. Now for all these changes, like how much do we gain? So we should mention on Bit Diffusion, where you model the discrete data. So having this self-conditioning actually help substantially, like improve things by a large margin. If you look at these two, on CIFAR 10, you have two discrete Bit Diffusion here. Now the blue bar is without self-conditioning, and green bar it is with self-conditioning. So you can see a huge drop of FID, which is smaller is better. So this is very important to use for the image discrete image generation. Now, if you apply this, because this is somewhat orthogonal to the analog bits, right? So you can also apply this on continuous or standard diffusion model, and it still helps significantly, maybe not as much as the Bit Diffusion here, from 47 FID to 6.9, but you still have a significant gain from like 8 to 4, something like that, right? Okay, so due to the time, probably I would ignore these parts where you can have several variants of self-conditioning and inference time, although the training will remain the same. Okay, now this is the self-guidance version. And the takeaway here is this difference, these variants have different sampling properties, but in general, the most basic one works quite well, except for this case where the self-guidance is better with larger sampling steps. Okay, so the final technique we propose in this work is asymmetric time interval. So as you might know, the time step plays a critical role in diffusion models. So during the typical diffusion, reverse diffusion process, symmetric time intervals are used for both state transition and time reduction. So what that means is the t in this denoising function here, xt in the state, and the time step t as input to the denoising network will be the same. They are shared. Now, when we're taking a larger step, asymmetric time t intervals, which result in this t being different, could actually be better. So this is an example with Bit Diffusion denoising here. So let's say you are at xt equal to t equal to 0.6, right? So you make a transition to 0.1. So this is a big transition because t is minimum is 0, maximum is 1. So you jump a lot, right? Now you take that at this state. Now you want to do the denoising. Ideally, if you denoise really well, you see the original image, which is the horse. But now you see a lot of noise because it doesn't denoise so well. So, but here we compare different t prime as input to the denoising network. As you can see here, the state is 0.1. If you input t equal to 0.1, it's doing fine, better than this. You denoise a little bit, but it is actually not as good as inputting t prime equal to 0.5. In this case, you're taking a symmetric time interval, right? So you can see here is an example that we're using a symmetric time interval could help. But how difficult is it for you to use it? Not difficult at all, because now you take the standard sampling algorithm, right? Now what you only need to add is a single adjustable hyperparameter, TD. It appears in here as an input to the generate function. And you just append it here. If it is 0, so that's the standard sampling procedure. Now, if you want to set it to 0.5, just go ahead and set 0.5, and then the procedure is just train the procedure. The rest is exactly the same. Okay. How well does it work? So I think again, this depends on the task. For image captioning, it turned out this is quite useful or important. If you look at here, when you have different sampling steps, and this is the blue score for the caption generated, the higher is better. So you can see if you use time difference equal to 0, which is the default sampling, the score is not as good as if you use something larger. So, but the point is that you can just change it on the sampling time without retraining the model. So this is something good to add to the toolbox. Okay, so putting it together, if you wanted to use this Bit Diffusion, what do you do? So this is a summary of the training and the sampling procedures. And I should say it's relatively easy if you already have a continuous diffusion code base. Now you only make a small twist to, tweaks to add these things into it. To conclude, we propose Bit Diffusion, a new family of generative models for discrete data based on diffusion models. It has some properties that counter the existing state-of-art autoregressive generative model. And I think it might be more scalable in especially cases where you have a really long sequence or high dimensional discrete data. In our paper, we show that the proposed method outperforms state-of-art autoregressive model and other discrete diffusion models in generating discrete images. And also it performs similarly to discrete autoregressive model in generating image captions. And yeah, that's all I have for the slides. Thank you very much for the attention. Maybe we can take some questions if there are any.
Okay, so thanks for giving this very interesting talk on the timely topic of diffusion models. So now we are entering the Q&A session where the audience can ask questions related to this talk about diffusion model in terms of the technical details, or you have broader questions about the trend or the the overall the direction in this area. So you can raise your hands by clicking the raise hand button in the reactions in the reactions button in the menu bar now. So feel free to ask any questions, please. Okay, we have Ziqi. I think you can directly unmute yourself. Yeah, you have the permission. Yes.
Yeah, sure. Thank you, Ting, for this talk. And I have a question regarding the analog bit. To my understanding, the image data is actually also discrete, which has from level 0 to level 255. And you convert this 0 to 255 representation into a binary representation using 0 and 1. So what is the reason for converting to this 0-1 binary representation? Is it because it can improve the sample quality or for some other reasons?
Oh yeah, that's a great question. So yeah, I should mention a lot of these images actually represent this U in 8, integers 0 to 255. But they have, if you model it as continuous data, is better because you have this ordinal relation. So although it is at different quantization level, but if you the distance between, let's say, 100 and 99 is much closer, compared to 120 or 180, right? Yes. So that means something. So the reason we select the discrete image generation as evaluation task is because not because this is a useful application. I think you should use continuous pixels, representation to model the pixels, as done in existing, continuous, diffusion model for generating beautiful pictures. But we wanted to evaluate, like, modeling this long sequence, complicated structure, comparing different models. We can obviously do with text, but evaluation on text is very involved. I mean, not as easy as evaluating on images. Like, people can quickly benchmark. Let's say you come up with a new idea, an improvement to bit diffusion, or completely different thing that you wanted to try. You can quickly test it on discrete image generation, get a score, right? Let's say you run on CIFAR 10 is doable in a single GPU. I mean, with several hours of training, but if you wanted to train a large language model, on 100, like 10K tokens, and evaluate it is not that obvious. So that's why we choose this discrete. And I guess many other existing work, they choose discrete image generation as a task of evaluation, under the assumption that if a model doing better on this kind of task, potentially when you transfer this to, let's say, modeling DNA sequences or modeling text in the future, so they could also do better. But I think in general, I think the application of these techniques would be somewhere besides image generation.
I see. So maybe image is just used for easy benchmarking, and the more promising application would be somewhere else.
Yeah, that's my feeling.
Yeah. Thank you. And also another question. So I find that you designed the network output to be X0, which is the data, instead of like in the original DDPM, the network output is epsilon, which is like the noise added to the data. So
right.
Is there any like specific reason for this choice?
Oh, I think that's just a hyperparameter, right? So you can predict either, and once you have either, you can transform it. So the reason that they perform different, I think, is rather specific to the choices we make in terms of how we model things and architecture and so on. So, but one thing we define, which is interesting, is for if you model continuous pixels like DDPM, yes, predicting epsilon is, I can actually go back to next slide. Predicting epsilon is better than predicting X on the data. So we're, yeah, so here you can see if you continuous data, if you predict the epsilon is better than predicting X. But if we go to discrete, bit diffusion, actually predicting the data X0 is better, significantly better than epsilon. It is still a bit mysterious, but I would just consider it as a hyperparameter. Practically, if you wanted to, you might want to try to play with it to see which is better.
I see. Thank you so much. That's all my questions.
You're welcome.
Okay, thanks, Ziqi. So we have a next question from, okay, I will lower your hands, Ziqi. So yeah, Yumin, you can speak up here.
Okay, thanks team for the nice talk. And along the Ziqi's question, I have so in my understanding that the key difference between the continuous data and discrete data is that in the continuous data, like the value 199 is closer to the 200, and in discrete data, there's no such relationship, right?
I guess I should clarify. So discrete data, they can be ordinal in the case where you have this relation preserved, or it can be categorical, which means every integer, the distance among integers, they are equal. So what you mentioned is more like the categorical setting. which is represented in the the uint random. In this case, this is kind of basically categorical setup, but uint 8, it partially preserves this order. Sometimes the order is it's completely not. So let me maybe go back to here, like this correlation. So the order is basically the difference in the intensity. So it roughly preserves the order, but you can see the variance is very large. Like in the gray code, you can have two binary codes only differ by 1 bit, but their actual differences can be quite large.
Okay, I see. So I think currently there are some work combining the VQ GAN and the diffusion model to do the image generation, and I think in their representation after the quantization, I think the tokens are kind of like the uint random one, because I think the codebook index 199 is I think there's no relationship between the 199 index codebook and the 200 index codebook. So my question is that do you think this technique is also works for that kind of method? Because in their method, they will train the diffusion model using the like the softmax loss, which is regard the task as a classification problem. So I mean,
I think yeah. So if I understand correctly, you are thinking like if we have VQVAE learn some latent discrete code, can we use similar techniques? Yeah, I think is yes. The answer is yes, but we haven't tried that on that kind of setup. So I guess so far the existing methods, if they use a discrete diffusion, they probably assume a discrete state space, which you can optimize with softmax, and then use categorical transitions among the states. So that's a different methods which we compare here. You can see like this D3PM uniform observing, they are basically the discrete state space, and we're doing much better in this modeling. So there's a reason to believe maybe in the latent space, if you have data that's not pixels, discrete pixels, but latent, our method might also work better, but we haven't tested, so we don't know. Another thing is, I think maybe the best way, I mean, I think I'm maybe not mistaken, but like, you can also model the continuous, like in a stable diffusion or this latent diffusion, right? So you have a continuous space, latent space, where you model with diffusion model. Like if you go to latent space, do you really want it to be discrete, or it can probably just be continuous? Like if you want to do like VQVAE, this kind of thing. So that's a question also. I mean, I know like this is a big trend or big family of methods based on VQVAE, but is probably, there's probably some limitation, compared to directly model the data instead of having model the latent and then mapping the latent to data, use a single decoding step.
Yeah, I see. Thanks for your answer. And I think maybe it is promising to use this method to do the VQVAE based diffusion model. I think we can have a try. Yeah, thank you for your answer.
You're welcome.
I don't have other questions.
Okay, thank you, Yumin. So any more questions from the audience? It's a very good opportunity to interact with world leading experts like Chen Ting about the about his research area. And if you're also interested in like self-supervised learning, you can also ask questions about that, because I think most of you have used or like know Chen Ting's work about the simple contrastive learning, right? SimClear. So you can, it's a very good opportunity. Okay, we got a question from the chat room how to raise hands. Yuan Han. Yeah, so the way to raise hand is if you see the uh, reactions option on your menu bar, right? You click it, and then you see the button of raise hand. Then you click the raise hands. Okay, so I will first lower the hands of Yumin. We got Yuan Han. Yes, Yuan Han, you can speak up directly. Yes, you can unmute yourself. Yeah.
Okay, so first, very thanks to Ting to give us a very great talk. And I know that you have done many great work on the pre-training like SimClear. However, I recently also done some research on this topic, but usually I can hardly get some useful feedback from the model performance on the downstream task. I really confused about why the design of my pre-trained work or some unsupervised learning design work or not. So do you have some suggestion about this, or do you have also face this problem, and how you solve this problem?
So if I understand correctly, you're asking how do you diagnose your pre-training model by the fine-tuning task?
Yeah, exactly. Because I think sometimes my model perform good on some tasks, but it not perform very good on other tasks. So and maybe one point better on a specific task can usually can tell me a lot about why I can gain 1 point performance on this test.
Yeah, I think it's a very good question, like how to diagnose this, machine learning model in general, right? So, and I mean, there's a good side and a bad side to it. The good side is now it usually requires some experience and the creativity, some conjecture and verification. So it's not as simple as, here is a general recipe and you guarantee to diagnose your model, with it the 100% of the time. So that's the good side. And then, that means AI researchers' job is difficult to replace because that's difficult. The bad side is, yeah, it is difficult. So you have to, I mean, it's the same side, like, you have to really looking into the signals that you're getting, like, if you have this task, it is performing really badly, like what's specific about this task? And I mean, first thing I will ask is there a bug, or if there's an issue with corruption in the data? If not, you look at what's special about this task, and maybe take different layers of the model. Maybe in the final layer is not as good. It doesn't mean the middle layer is not as good, or model from different stages of training. So is it improving and then decreasing, or so I think there are a lot of things one can do, and that really depends on the exact situation you are in. And I think a lot of it probably requires some creativity, like imagination on what could possibly go wrong. But just regarding to like downstream and the pre-training, I think a lot of it might have to be a bit more correlated. I think especially for language domain, you have this pre-training like GPT, right? Or Palm from Google. A lot of these large language model, they are fine-tuned, or they don't even need fine-tuning. They just do this prompting to solve different tasks, and they are able to do it because the pre-training and the fine-tuning might be quite similar. Like a question you ask in the not fine-tuning, like a zero-shot testing, right, or prompting, could very much be very similar questions and answers have been presented in the pre-training, because you have web internet data, like there are some question and answers. So I think that's a very good, they will just generalize out of the box. But for computer vision, I think a lot of cases it's not like that. Like detection is very different from segmentation, and very different from maybe similar to captioning, but for key point detection, maybe it's very different from classification. So if we have a somewhat unified interface that you can express all these tasks together, only then you can somehow like expect a generalization, kind of like what language model does to language task. Like a generalized out of box, you can solve all the task by just prompting it, given a few examples. Yeah, that's what we were doing with what we are doing with pixel to sequence, where you can formulate a set of vision tasks, from pixel to semantically enable meaningful sequences, and this interface might be able to allow more generalization between different tasks, and then also the possibility of the pre-training and the zero-shot prompting can be can be as natural or as straightforward as in language models.
Yes, I agree that I think maybe the future of the pre-training and the fine-tuning is try to close a gap between these two stages, right?
Yeah.
Yeah, thank you a lot.
Okay, so yeah, thanks for the insightful discussion. So I have a question about the area of generative modeling. So Chenting, I can see you have also worked on GAN before, and then now you are working with a diffusion model. So what do you see is why, like in recent, especially like in these 2 years, why people shift from GAN to diffusion model? What do you see? What's the key here?
Yeah, I think diffusion, just because diffusion model work better, right? If you have something else, like if there's another technique that also enable GANs to work as good as well as diffusion model, people should shift to that as well. I think is fundamentally, I think they are quite different, and to me, I found the diffusion through a path that I kind of start thinking similar ideas, and then eventually converge to what diffusion model it is doing. And then I think like the aspect of iterative refinement is really interesting, aligned with how at least I think a lot of people perceive the world. Like you gradually refine your answers, or when you're writing papers also doing similar things. So I think that's very good intuitive approach. But there are also some issues with diffusion models, obviously. Compared to GANs, they have quite a lot of benefits, like the flexibility, also more stable, easier to train. In terms of scalability, they are all things to be more scalable. So yeah, I think mainly is the results that they can deliver make people so excited about them.
I see. So thanks. So yeah, so last chance, any more questions from the audience? You can raise your hands, or you can type any question in the chat room. It's a great opportunity. So if no, we probably can end the session here. So thanks again, Chenting, for the wonderful talk and the and insightful insightful discussions here. So thank you everyone for coming, and we will see you in the next episode of the AI Talks. So if you want to stay, we also have a like private session after this Q&A. If you want to stay here to talk with Chenting for more, you can stay. Otherwise, you can leave the room. So thank you to all. Bye bye. Thank you.
Thank you.